Hi everyone, Dr. Burns here with our first lesson in Chapter 6, Representing Molecules. In this lesson, we're going to talk about the octet rule, electronegativity and polarity, and how to draw Lewis structures. So let's begin. Now we've talked about this before in our previous lessons, but just to review, according to the octet rule, atoms will lose, gain, or share electrons in order to achieve a noble gas configuration. Remember, this is the octet rule, so this is 8 because 8 is great. Atoms would prefer to have 8 electrons around them. So here we have the bonding scheme of F2. So each fluorine atom in F2 has 7 valence electrons, where one of those electrons in each of them is unpaired. Now, because both fluorines have 7 valence electrons and they're 1 electron away from having a full octet, or 8 electrons around them, what these two atoms are going to do is share those electrons so that they can each claim 8 electrons. So the fluorine here in red gets to claim these 8 electrons, and the fluorine with the blue electrons gets to claim those 8. The two that are overlapping between them were the unpaired electrons, but now they are paired up. Think of it like a puzzle, right? If you have a puzzle piece, these two are going to fit together and stay together and form a bond. So, only valence electrons will contribute to bonding, and this is specific for covalent bonding. Because fluorine is a nonmetal, so it's a nonmetal with a nonmetal. And if electrons are shared, that means it's a covalent bond. If electrons are donated, that is an example of ionic bonding, which is what we discussed in our previous chapter. So, since valence electrons are the only electrons that participate in bonding, we have to remember how to determine our valence electrons. So let's do a little bit of review from our previous chapters. How many valence electrons are in one oxygen atom? So I'm looking at oxygen by itself, only one oxygen. Look to your periodic table because our periodic table can help us remember how many valence electrons there are in each atom. If you find oxygen on your periodic table, you'll see it's in group 6, group 6A, or group 16, which tells us the number of valence electrons because our group number with the A after it is equal to our valence electrons. So, since oxygen is in group 6A, it has 6 valence electrons. Remember, if you're looking at the group number where it's in the teens, we have to take that number and subtract 10 so that we get our number of valence electrons. And if you think about it with oxygen, oxygen is element number 8, so it has 8 protons and 8 electrons. It simply cannot have 16 valence electrons because there's only 8 electrons in oxygen overall. So that's why we have to remember to subtract that teen value by 10, which is why it's also useful to look at the group number where it has the A after it. Okay, so let's quantify how our electrons are participating in bonding using the octet rule. So what we were talking about with fluorine F2 previously, only 2 of its valence electrons were participating in the formation of the F2 bond. So remember, just these two valence electrons were the ones that formed the bond. The pairs of electrons in a bond, or that form a bond, are called a bonding pair. So this pair right here is a bonding pair. And we typically show our bonding pairs in structures as a line. Our line represents our two electrons that participate in the bond formed between the two atoms. You can think of it like here's an electron, there's two electrons there, and we connect the dots to form a bond. So if the electrons are in a bond, they are considered a bonding pair. Fluorine had 7 valence electrons, but only one of them was a bonding electron, right? Only one electron came from each fluorine to form the bond. Therefore, the other 6 valence electrons were not a part of the bond formed. So we call those lone pairs. So the little dots of electrons on the outside of each of these fluorines, okay, since they're paired up, those are our lone pairs. And remember, we're talking about pairs. So pairs mean 2, so 2 electrons. A bonding pair has 2 electrons, and a lone pair has 2 electrons. The lone pairs are just the valence electrons that are not participating in the bonding of that molecule. So to represent molecules where we show their bonding and their bonding pairs and their lone pairs, we can start drawing Lewis structures. And a Lewis structure is a representation of covalent bonding. Okay, this is only for covalent compounds. So this will be 2 or more nonmetals. We don't have Lewis structures for ionic compounds because they're not actually forming a bond. A bond occurs when there is electrons being shared. If the electrons are not being shared, then there's no bond being formed. And in ionic compounds, the electrons are being donated. So the two atoms are being attracted by their difference in charge. That is not happening here with covalent compounds. The electrons are being shared. Therefore, we have bonds, and that's how we represent our bonds, is through a Lewis structure. So the shared electron pairs, so those bonding pairs, the electrons that are shared between the two atoms forming the bond, are shown either as dashes or as pairs of dots. So here we have water, H2O, and its Lewis structures. H2O has a bond from the oxygen to the hydrogens, and we show those with these 2 electrons here. I'll change color so it's a little bit easier to see. We have 2 electrons here, 2 electrons here. One of those electrons came from the hydrogen, and one of those electrons came from the oxygen. Okay? So these would be our bonding pairs. Okay? The lone pairs are shown as just dots on the individual atom. So oxygen has 2 lone pairs, which I'm highlighting in blue, that are just associated with the oxygen itself. Okay? So these would be our lone pairs. Our lone pairs can have another name, and that is non-bonding pairs. Because they are pairs of electrons that do not participate in bonding. So we show our shared electrons, our bonding pairs, as either dots or dashes. So here's those dashes, let me represent them in red. Here's those again, those are our bonds, and our lone pairs are just pairs of electrons on our central atom. We want to designate the difference between bonding and non-bonding pairs, which is why we typically show them, show structures more in this fashion, where we show the bonds as dashes and the lone pairs as dots. So we can say that these electrons are in fact non-bonding, and these electrons are bonding. So I'm going to be drawing these structures for the remainder of this lecture outside of some of our practice problems in this form, where I have my shared electrons as dashes and my lone pairs or my non-bonding pairs as dots. Okay, so we also have to discuss multiple bonds, how multiple bonds are represented in Lewis structures. So in a single bond, which is what we have been looking at, the atoms are held together by one electron pair. So in water, again, here's that one electron pair that's holding together the two atoms or creating the bond. A double bond then has atoms that share two pairs of electrons. So I'm going to try to color code these. We have one pair on each side. For this is carbon dioxide, so this is CO2. Okay, so they have one pair on either side, and then they have another pair on the other side. So they are made up of two pairs of electrons, and those are both bonding pairs. So we have two bonding pairs that make up a double bond. We show double bonds as two dashes parallel to each other going between the two bonds. Okay, so we show them as a way to connect them. Again, think of it like there's 4 dots here and you're connecting those dots to form the double bond. So we draw them to connect the two atoms. And then again, our lone pairs are shown as just dots on the individual atoms. Our last type of bond is a triple bond. And a triple bond occurs when atoms are held together by 3 electron pairs. 3 electron pairs. So double was 2, triple is now 3, and that's where we're going to end it. We don't have any quadruple bonds or anything like that. We only go from single, double to triple bonds. So this is 3 electron pairs, so let's highlight those 3 electron pairs. There's one here, and then there's another one there. We'll use green to show our last one. So we have 3 bonding pairs that make up a triple bond. And we show triple bonds now as 3 parallel lines that connect the two atoms. Again, because it's like we have 1, 2, 3, 4, 5, 6 electrons that are participating in the bond. So they just connect those dots. Okay. So let's practice this. You'll see similar problems like this on your ALEKS homework. And what we want to do is using these Lewis structures where we show our bonds as dots, as well as our lone pairs on dots. As dots, we want to count our bonding and our non-bonding pairs. So what I'm going to do is I'm going to use my highlighter here, and I'm going to say anything that's highlighted in blue is a bonding pair. And anything that's highlighted in red is a non-bonding pair, also known as a lone pair. They're not participating in the bond. So these would happen between atoms, and these are on one atom. Okay. So let's do our first structure. We're going to try to identify our bonding pairs first. So we have CO2 here. So we have bonding pairs. I'll try to zoom in here. Is that going to be too large? It is. Let's get a little smaller. So we have CO2. We have a bonding pair here and a bonding pair there. That's between the carbon and the oxygen. On the other side, we also have a carbon and an oxygen. So there's a bonding pair there and a bonding pair there. For our non-bonding pairs, they're going to be localized on just the individual atoms. Carbon doesn't have any, okay? All of its electrons are in their bonds. So oxygen has 2 non-bonding pairs on each of those. So those non-bonding electrons are not in between the oxygen and another atom. They're just localized on the oxygen. So CO2 for bonding pairs has 1, 2, 3, 4. Remember, this is pairs, so we're counting by twos. And non-bonding pairs, it has 1, 2, 3, 4. We can always double check because we know that this is in total 8 pairs, which is equal to 16 electrons, right? Because each pair is 2 electrons. So we can count those up and say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 electrons that we are representing. So we have properly accounted for all of our pairs of electrons in this structure. So let's move on to our next one. Okay, it's a little bit more complex, so let's just go in and start figuring out our bonding pairs. So in blue, I'm going to highlight any pairs of electrons that are between atoms. So let's start from the left. We'll go between oxygen and hydrogen. There are 2 electrons that are shared between those 2 atoms. On the other side of oxygen, between oxygen and carbon, we have another 2 electrons. And then after carbon, in between the next carbon and oxygen, is another 2 pairs. The pair over here is not in between an oxygen and another atom, so it is not a bonding pair. Above the carbon, we have some pairs between the oxygen and the carbon. So we have a pair here and a pair there. Okay. Next up, we're going to look for our non-bonding pairs, and those are going to be the pairs of electrons that are not in between 2 atoms. So that's every other pair that we see. So oxygen has 2 pairs that are localized on itself. The other oxygen on top here also has 2 electrons. And our oxygen on the very end has 3 pairs of electrons. So let's count those up. Our bonding pairs, we have 1, 2, 3, 4, 5. And our non-bonding pairs, we have 1, 2, 3, 4, 5, 6, 7. Let's just double check our work. 5 plus 7 is 12 pairs, which should equal 24 electrons. So let's count those up. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We have all of our 24 electrons accounted for. Awesome. Let's do another example. Okay, again, let's start off by finding all of the electrons that are in between atoms. So in between the carbon and the hydrogen, there's pairs on both sides. And in between the carbon and the oxygen, there's pairs on both sides. That's it for our bonding pairs. And our non-bonding pairs are just localized on the oxygen. They're not in between any other atom in that oxygen. They are strictly around the oxygen itself. So our bonding pairs, we can count up. We have 1, 2, 3, 4. And our non-bonding pairs, we have 1, 2. Okay, so that's a total of 6 pairs, which is equal to 12 electrons, which we can count up and see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All 12 electrons are accounted for. So we should always double check our work. Okay, So we have two more examples down here. Let me highlight them here. Oops, highlighter's too small now. There we go. We have these two examples down here. What I want you to do is pause the video and try these last two examples on your own. Okay, let's zoom in and see what we can do for each of these. I'm just going to erase some of this so we can highlight it. Okay, so let's start off by looking for our bonding pairs, and those are going to be the pairs of electrons that are between our atoms. So we have a pair in between our carbon and our hydrogen. And then on the other side of carbon, we have three pairs of electrons that are between the carbon and the nitrogen. For our non-bonding pairs, we just have one on our nitrogen there. So let's add these up. Bonding pairs, we have 1, 2, 3, 4. And for non-bonding pairs, we just have 1. This is a total of 5 pairs, which would equal 10 electrons. So let's check our work. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. And let's jump to our last example over here. Okay. So let's count up our bonding pairs first. We only have 2 atoms in this molecule, so it's any pairs of electrons between those 2 atoms of nitrogen. So we have 1, 2, 3. Those are the only pairs that we have in between our nitrogens. On the opposite side of each nitrogen, we have our non-bonding pairs. So in total, we have bonding pairs 1, 2, 3. And our non-bonding pairs, we have 1, 2. We should always check our work, so that's 5 pairs. That should be equal to 10 electrons, which we can count up and see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. Awesome. So we can see through these molecules that we can identify our bonding and our non-bonding pairs. In many of these, we saw our multiple bonds. So here we have some double bonds. Okay, we even had a double bond here. Here's another double bond. We also had some single bonds. We have multiples of those in that molecule. Finally, in our last 2 examples was where we saw triple bonds. Because we had 3 pairs of electrons holding two atoms together. So there were 3 pairs of electrons in between those nitrogens, so they make a triple bond, which we also saw over here between this carbon and nitrogen. We have a triple bond. Okay. So now that we can make those bonds, now we know how those bonds are being made and what makes up those bonds, we can talk about the electrons within those bonds themselves. So there are 2 extremes in the spectrum of bonding, which we have talked about in our previous lessons. First is covalent bonding. Covalent bonds occur between atoms that share electrons. Remember, that's our big difference between covalent and ionic bonds. Ionic bonds occur between a metal and a nonmetal, and those involve ions. So we can even break this down further. We share electrons, and these are between nonmetals for covalent compounds. And for ionic bonds, they're between a metal and a nonmetal and involve ions because electrons are donated from the metal to the nonmetal, because that's our cation and our anion. So it's always good to remember those differences. So let's review that just to make sure that we are 100% positive we know the difference between covalent and ionic compounds. So determine if the following are ionic or covalent compounds. So our first one is MgSO4. Well, SO4, that's one of our polyatomic ions. So it's a polyatomic ion, and it's paired with an Mg, which is a magnesium. So we have a metal and a nonmetal because our polyatomic ions are nonmetals, right? SO, sulfur and oxygen are nonmetals. So this would be an ionic compound. Because it is between a metal and a nonmetal polyatomic ion. Next up, we have CCl4. C is carbon and Cl is chlorine, so we have carbon and 4 chlorines. Let's find those on our periodic tables. They are both on the right side of our periodic table, meaning they are both nonmetals. So if they're both nonmetals, this is a covalent compound. Okay, try our last 2 examples on your own. Pause the video, try those last 2 on your own, find them on the periodic table, and then come back to our video to check your answers. For our next example, NH3, we have to remember that hydrogen is a nonmetal, even though on some periodic tables it is placed in the first row or first column, but hydrogen is a nonmetal because it's a gas. So if hydrogen is a nonmetal and nitrogen is also a nonmetal, this would be a covalent compound. Our final example is NaCl. Na is sodium, Cl is chlorine, so this is sodium is a metal and chlorine is a nonmetal. So this would be an ionic compound. Okay, good review. So the bonds that exist between these elements, between these atoms, can be quantified as something called polar. Now, a polar bond means that although the electrons are shared, they're not being shared equally. So one atom may be pulling the electrons more towards itself than the other atom. Okay, it's kind of like a tug of war of electrons. So we have 3 different ways to quantify our bonds. The first one is pure covalent bonds. This is when the electrons that hold the 2 atoms together are being shared equally amongst both of those atoms. Okay, so they are being shared equally. In a polar covalent bond, I should say that a pure covalent bond is often referred to as a nonpolar covalent bond. That's another term that we will use, as well as in your ALEKS homework. You'll see it referred to as a nonpolar covalent bond, which means it's purely covalent and the electrons are being shared equally. In a polar, so keyword there being polar covalent bond, this means that the electrons are being shared unequally. So one atom is pulling more electrons than the other from that bond. And we show this with partial charges. So this little delta symbol that we see here, this means partial charge. So in the case of what we have here, we have a partial positive and a partial negative. So one side, this has more electrons than the other. So the electrons are being pulled towards the partial negative rather than the partial positive. Because the electrons are being pulled towards one, it creates an area of more negative and more positive portions. Finally, we just have an ionic bond, and this is just when we have opposite charges. So this is going to be any metal and non-metal interaction. So just like we were doing before, if we can quantify something as a covalent compound or an ionic compound, well, if it's ionic, it's strictly an ionic bond. If it's covalent, we then have to quantify it further by saying if it's nonpolar or if it's polar. So that's what we're going to talk about here. So we can see how the electrons are being pulled differently through these electron density maps that showed the distribution of the charge in different compounds. So the red is where electrons are, so red is negative, and blue is positive, an area of more positive portions. So in our first example, we have H2, which is a nonpolar covalent compound. So the electrons are being shared equally. So we see all of the electrons right in the center of that atom. Okay, so here's the H, here's the H, the bond is here, and the electrons are shared perfectly in the middle of those two atoms. Okay? In our polar covalent example, we have HF. So I have H here and F over here. And if we remember our fluorine atom, when it makes a bond, only one of its electrons is forming the bond. The rest of them are represented as lone pairs, okay, as dots around it, which means we have a lot of electrons over there. So that's why we see the electrons more on one side, on the side of the fluorine, than the hydrogen side. So when we say we have a partial positive and a partial negative, that's what we mean. The electrons are just spending more time over there. So we can show an arrow that points to the more negative side of that atom. Finally, we have our ionic representation. Again, this is just a cation and an anion, so this is purely negative because that element has more electrons. Okay, it has all of its valence electrons, whereas the cation has no valence electrons. So there would be no red on that side. Okay, so the electrons are not shared. They're literally just two little magnets sticking together to create an ionic bond. Okay. So we quantify that relationship between the electrons, the pull of the electrons, using something called electronegativity. And electronegativity is the ability of an atom in a compound to draw electrons to itself. And electronegativity has a trend on the periodic table that varies with atomic number. So just like we saw electron affinity and ionization energy having different trends based on how much something wants an electron, or wants to give away an electron, electronegativity has a similar trend. So, electronegativity, the most electronegative atom is fluorine. Okay, that's the most electronegative, and it has an electronegativity value of 4. So our chart here, which is also in your lecture pack, it has all of these values on it for the individual electronegativities of those atoms. Okay, so 4 is our highest electronegativity and 0 would be our lowest. So 4, the higher the electronegativity, the more the atom wants electrons. So higher electronegativity means more pull of electrons in a compound. And we see from this electronegativity chart that our nonmetals have really high electronegativity. So here are our nonmetals, right? These guys are our nonmetals. And our nonmetals typically create anions, okay, which means they take on electrons, which corresponds to their higher electronegativities. Our metals have lower electronegativities in comparison because they typically give away electrons. And form cations, and that's why they have the positive charge. Okay, so there's no sharp distinction, no specific distinction between nonpolar covalent and polar covalent bonds, or even between covalent and ionic bond, or polar covalent and ionic bonds. There really is no difference in terms of specific atoms that form those types of bonds, but we can have some rules that generally help us distinguish the difference in bonds. And it looks at their difference in electronegativity. So we look at delta En. So that's the difference in electronegativities. Okay, so if the bond between two atoms whose electronegativities differ, so have a delta En, less than 0.5, this is generally considered a pure covalent or a nonpolar covalent bond. If the bond between atoms whose electronegativities have so their delta En, again, is different by a range of 0.5 to 2.0, then they are typically polar covalent. So polar covalent bonds. Finally, if the bond between two atoms whose electronegativities differ by 2 or more, this is generally considered ionic. Now there is an exception to that, and that is we see this specifically with fluorine. And another nonmetal. Okay, sometimes that difference, that delta En with fluorine, since fluorine is so electronegative, if fluorine is bonding to another nonmetal, the delta En is sometimes greater than 2.0, but this would still be considered a polar covalent bond because fluorine with another nonmetal is a covalent compound. So this is where we have to keep in mind that our first definition of what's covalent versus what's ionic. If it's a covalent compound, the only two options for types of bonds are either nonpolar or polar. If it's ionic, if it's an ionic compound, the only option for a type of bond is an ionic bond. Okay, so if you have an example where it's fluorine with another nonmetal and you get a delta En of greater than 2, this would still be considered a polar covalent bond because it's a covalent compound with a very electronegative fluorine. That fluorine is just pulling all of the electrons to itself because it is the highest or the most electronegative atom on the periodic table. Okay, so there are some exceptions to this. This is why we use the word generally throughout. So just keep that in mind. So let's do a little bit of practice with this. So I have our electronegativity chart here on the screen with me, and you have it in your lecture packet as well, so feel free to utilize that. We want to determine if the bonds between the following elements are either nonpolar, polar, or ionic. And if they are polar, we need to determine the more electronegative atom. So let's start off with a Cl, or a chlorine-oxygen bond, so Cl to O bond. So we need to find our delta En. So we're going to look to the electronegativities of chlorine and oxygen. Chlorine has an electronegativity of 3.0, and oxygen has an electronegativity of 3.5. Now, when we're doing delta En, think of this as an absolute value. We can't have a negative electronegativity, so we're really just taking the absolute value of the difference. So this would be 0.5. The delta En is 0.5. If we go over to our little chart here that tells us how to tell the difference between the electronegativities, if it's between 0.5 and 2.0, this would be a polar bond. And in this case, oxygen is our more electronegative atom because its electronegativity is higher than chlorine. So oxygen has an electronegativity of 3.5, whereas chlorine has an electronegativity of 3.0. Okay, let's try the chlorine-fluorine bond, so Cl and F. Let's try that one. Delta En of chlorine and fluorine. Well, chlorine we know is 3.0, and fluorine is 4.0. So the difference, the absolute value of that difference, is 1.0. That again falls in our range of 0.5 to 2, so this would also be a polar covalent bond. Okay. Next up, we have the double bond in C2H4. So I'm going to draw this structure for us. So C2H4 has a double bond between the carbons. So it's talking about the carbon double bond in C2H4. It then has two hydrogens coming off of it. And what we're going to learn in the later half of this lesson is how to draw these structures. So don't worry about not knowing how to draw the structure right now. We'll get there. So we want to look at the carbon double bond in C2H4. So we want to look at the electronegativity difference in this bond right here. So we take our delta En and we just look up the electronegativities of both atoms in that bond. Both are just happen to be carbon. So the electronegativity of carbon is 2.5. So we take 2.5 and subtract off 2.5. And we get an electronegativity difference of 0, meaning this is a nonpolar bond. Bonds that are between the same atom are always nonpolar. So if you have like an HH, FF, a CC, anything like that, so on and so forth, whatever you have, if it's the same atom, the electronegativity difference is always going to be 0, and it'll always be nonpolar. Now in this example, I also want to highlight our multiple bond example. So we have two bonds here. The fact that there's multiple bonds does not change how the electrons are shared. So multiple bonds don't affect the electronegativity or polarity of the bond. So it doesn't matter if there's a double bond, a single bond, or a triple bond, whatever it is, we're only looking at the difference between the two atoms that are bonded together. It doesn't matter how many bonds it takes to bond them together, it just matters what those atoms are. And if they're the same, then it's going to be nonpolar, regardless. Okay, our last example, I have a little bit of room down here, is the CS-Br bond. And to see CS, I think I have to erase some of this. So let me just correct that. This is polar. Okay. So CS and Br. CS is all the way down there. That's cesium. And Br is over here. That's bromine. Now, because they're on two different sides of the periodic table, we have a metal and a non-metal. We know that this is automatically going to be ionic. This is an ionic compound. Meaning it would automatically be an ionic bond. But we can use our electronegativities to prove that to us. So we can look at delta En. We take the cesium, 0.7, subtract off the 2.8. Again, this is an absolute value because we can't have a negative difference, and that difference is 2.1, meaning it's ionic. Now there are some cases where, as we get kind of into our metalloids and our transition metals, yes, those delta E's may fall into the polar-nonpolar range, but we have to remember our first designation of, is it covalent? It's only covalent. It can only be a nonpolar or polar covalent bond if it's a covalent compound. If it is an ionic compound, the only option for type of bond is ionic. So we have to do that designation first. It's almost like a hierarchy. We first have to determine covalent or ionic, and then we can go into type of bond, which would then be nonpolar, polar, or ionic. Okay, so the first one, determining if it's covalent or ionic, comes first, and then we determine the type of bond. If it is ionic, the only type of bond that it can be is ionic. Okay, let's practice a few more. Here we have the structures given to us, and we have to determine if the bonds are polar, nonpolar, or ionic, but we have to do it for each type of bond. So in our previous example, we really only looked at, one atom bonded to another. Okay, we looked at, diatomics, or we didn't look at an entire molecule. Here we're going to look at, okay, what about the CO bond? What about the CH bond? What about the CN bond? What about the CS bond? We have to look at both of those electronegativity differences to determine if those bonds are polar or nonpolar. And we may see that in some molecules we can have both polar and nonpolar bonds. So let's look at our first example. Let's look here. COH2. So you can choose whichever one you want to do first. We'll start with the CH bond, I guess. So we're going to look at our delta En, and we're going to find our electronegativities of hydrogen and carbon. So we look over here, we have carbon is 2.5 and hydrogen is 2.1. So we take 2.5, subtract off 2.1. Again, it doesn't matter the order that you do it in, you're going to do an absolute value anyways. So this would be 0.4, which would be nonpolar. Okay. Now this would also apply to this carbon-hydrogen bond because the electronegativities are going to be the same, so this would also be a nonpolar bond. Next up, let's do the CO bond. So we want to take the electronegativity difference of C and O. We already know that C has an electronegativity of 2.5. We just have to look up oxygen. If we go to our chart, oxygen has an electronegativity of 3.5. So we're going to take 2.5, subtract off 3.5. Again, it's an absolute value, so we get a difference of 1.0, meaning this would be a polar bond. So our molecule here is made up of, let me erase it to make it a little bit clearer. This is made up of a polar bond and two nonpolar bonds. So we can have that difference in bond polarity within the same molecule, okay? What we're not going to do is look at the difference between oxygen and hydrogen because they're not bound together. If there isn't a bond between the two atoms, then we don't need to find the electronegativity difference. We don't need to determine if the bond is polar or nonpolar because there's no bond formed. Okay, let's look at our next example. CS and CN. So if we look at our CS bond, our delta EN. Well, we know carbon. Carbon was 2.5. Let's look up sulfur. Sulfur is also 2.5. So we have an electronegativity difference of 0. So this would be nonpolar. And then if we do our carbon-nitrogen, our delta EN, carbon is 2.5. Subtract off nitrogen. Nitrogen is 3.0. That leaves us with a 0.5 for an electronegativity difference, meaning that we are polar. So in this atom, and in this molecule, we have a nonpolar bond and a polar bond. We even see this in the structure. The structure even has a negative on the nitrogen because that nitrogen is pulling all of those electrons to it through its polar bond, meaning that negative charge sits more on the nitrogen than it does any other atom. Okay. So our last one is this N2 with a triple bond, and we know that if it's two of the same atom, the electronegativity difference is going to be 0, which we can prove because the electronegativity of nitrogen is 3.0, and the difference of that is 0. So we know that this is a nonpolar bond. Okay, so the electrons are being shared perfectly in the middle of those two atoms. Okay, so let's get into drawing these structures. How do we classify our structures? How do we draw them? Everything like that. So, as we said before, a Lewis structure is a representation of covalent bonding. That's a big word right there. Covalent bonding, in which shared electron pairs are shown either as dashes or pairs of dots between two atoms, and lone pairs are shown as pairs of dots. Now, like I said before, I'm going to prefer the dashes for shared pairs and the pairs of dots for the lone pairs, just to make sure we know the difference between bonding and non-bonding pairs. So we have again our structure of water, which we've looked at before. Now, in order to draw these structures properly, we have to follow a certain set of guidelines to make sure that our electrons and our bonds are being represented properly. So we can't just say that we know where the bonds are going to go. We can't just make random bonds places. We have to follow a set of guidelines to draw them. So the guidelines are here below, and I believe in your lecture notes you have to copy these steps down. So copy these guidelines down as we go through them. So our first step is we want to count the valence electrons. Remember, our valence electrons, we look to our group number on the periodic table. That tells us our valence electrons. We have to count the valence electrons of all atoms in the molecule. All of the atoms in the molecule, we have to count up their valence electrons. We then have to draw the skeletal structure with our bonds are our electron pairs, our bonding pairs, between the central atom and the surrounding atoms. So our central atom, if I were to draw this kind of on the side, is X, and our surrounding atoms would be Y. And our shared electrons, our bonding electrons, are the dashes in between. Okay, so all those dashes show the bonding electrons. Once we have drawn our skeletal structure and have shown all of our bonds with dashes, we subtract the bonded pair electrons from the total number of electrons that we had overall. The idea here is that every atom is contributing its valence electrons to form this structure. So we think of the electrons going into one big pot, and then we're essentially distributing them evenly throughout the entire molecule because those electrons are being shared. And we're distributing them first as bonds, and then what we'll see is we're then going to distribute the rest as lone pairs. So our next step after we subtract the bonded electrons from the total number of electrons, okay, we're going to place any remaining electrons as lone pairs to complete octets, and that should be specific to our surrounding atoms. So on the surrounding atoms first. So we're placing any remaining electrons as lone pairs to complete octets on the surrounding atoms first. So that would be like our Ys. So these are our surrounding atoms. Now we also have this thing called duets at the bottom. Duets, if you recall from the last time we talked about the octet rule, this was specific atoms can only have 2 electrons around them. We're going to see this specifically in hydrogen. It will only take on 2 electrons. Okay, so hydrogen will typically only form 1 bond. And this is just because hydrogen only has 1 proton, so it can't balance out a full octet of 8 electrons when it only has 1 proton. That would be far too negative for it, and those electrons would just repel each other and wouldn't balance well with the 1 proton. So hydrogen will only have 2 electrons shared with it. Okay, so after we've completed our octets on our surrounding atoms, we're going to subtract the amount of electrons that we used to do that from our total. If we have any remaining electrons after our octets are complete on our surrounding atoms, we're going to place those remaining electrons as pairs on the central atom. Okay, so that would be the X. That's our central atom. That's this atom in the center. Finally, if all of the electrons are gone and we still do not have octets on all of our atoms, that is when we are going to form multiple bonds, and we're going to do that by moving electron pairs. Now, these guidelines, as they are written, are very useful, but they're not very useful right now because we haven't shown how to use them. So the best way to understand these guidelines and know how to utilize them is through practice. So we are going to practice a lot of structures, and we are going to practice using these guidelines to draw those structures. So let's start out with a few examples. So our first one is CH4. Our first step, we have to count our valence electrons of all atoms in the molecule. So we look to our molecule at CH4. That means I have 1 carbon. That carbon has 4 valence electrons, okay, because it's in group 4A, so it has 4 valence electrons. We then have hydrogen. Hydrogen has 1 valence electron, but there's 4 of them. So we take the 1 valence electron and we multiply it by 4, okay, because there's 4 of them. So in total, CH4 has 8 electrons that it is going to share amongst the structure. Okay, so we completed step 1. Moving on to step 2, draw the skeletal structure with bonds between the central atom and the surrounding atoms. So how do we know what our central atom is? Well, whatever atom is first is our central atom, and whatever atom is second are our surrounding. There are some exceptions to this, and that would be if hydrogen is first. Hydrogen can never be a central atom. So sometimes we have structures where H comes first. That will not be a central atom. So we typically read from left to right, and that's the way we look at these. So central atom is first, and then surrounding atoms come second. So our central atom here is carbon, and the surrounding atoms are then hydrogens. Now these are Lewis structures, so I'm going to follow similar rules as my Lewis symbols, where I'm going to represent kind of like a square. I'm going to put those hydrogens on all 4 sides of my carbon square, right? So we put them all on one on each side, okay? And then we're going to connect them to our central atom using bonds. So step 3 then says to subtract the bonded pair electrons from the total. So what that means is I've used up electrons to form the bonds. I now have to count up how many I used and subtract that from the total that I had. So how many electrons did I use to form these bonds? Well, each bond has 2 electrons. So that's 1, 2, 3, 4, 5, 6, 7, 8. I used 8 electrons to form my bonds, so I'm going to subtract that from my 8 electrons that I had total, and I have none left. Since I have no electrons left, I don't follow steps 4, 5, and 6. I don't need to, okay, because I don't have any remaining electrons. The last thing we can do is just double check that our octets are complete. So carbon has how many electrons associated with it? Well, because these are bonding pairs here, those electrons are being shared, and so carbon can claim all of them. So it can claim 1, 2, 3, 4, 5, 6, 7, 8. So carbon has 8 electrons around it. And hydrogen, each hydrogen has 1, 2 electrons. And remember, hydrogen forms a duet, so it will only take on 2 electrons. So our octet for carbon is complete, and our duet for all hydrogens is complete. So our structure for CH4 is C with the 4 hydrogens around it, each with a single bond. Okay, let's do another one. Let's follow our steps for our next example. Our next example is CH2Cl2. So that's our compound. We want to then draw its structure. So our first step says to count the valence electron of all atoms in the molecule. So we have to count our valence. There's 1 carbon. Carbon has 4 valence electrons because it is in group 4. There are 2 hydrogens, and each hydrogen has 1 valence electron. So we just take that 1 and multiply it by 2. Finally, we have chlorine. Chlorine has 7 valence electrons because it is in group 7, or group 7A. But there's 2 of them, so we're going to multiply it by 2. Okay, so now we have to add that up together. Feel free to use your calculator. It is always fine to use calculators on these simple types of math because you never want to be missing electrons. If we add up our total number of valence electrons in CH2Cl2, we get 20 electrons. Okay, so that's step 1. We've completed step 1. We've counted all of our valence electrons. Next up, we want to draw our skeletal structure with bonds between the central atom and the surrounding atoms. Well, remember, we read from left to right, so our central atom is carbon, and the atoms that surround it are going to be 2 hydrogens and 2 chlorines. Okay, remember this is like a box, so they can go on either side. Since there's 4 atoms in total, they fit on all 4 sides. And then we're going to connect those surrounding atoms to our central atom with bonds. So that was step 2. Step 3 says to subtract the bonded pair electrons from the total number of electrons. So I had 20 electrons total. How many electrons did I use to make those bonds? Well, each bond has 2 electrons in it, and if I made 4 bonds, I used up 8 electrons. So I have 12 electrons left over. So we finished step 3, and now we can move on to step 4, where we place remaining electrons. So I have 12 remaining electrons that I'm going to place as lone pairs on my surrounding atoms to complete their octets. So hydrogen does not need any lone pairs because it already has 2 electrons associated with it, and that completes its duet, so it's happy. So hydrogens are happy. The chlorines, on the other hand, only have 2 electrons associated with it, so we need more electrons to complete its octet, specifically 6 electrons. So we can put those as lone pairs, 1, 2, 3, 4, 5, 6 on the chlorine. That way when I look at this chlorine, it has 8 electrons. Okay, the same can be done to the other chlorine, 1, 2, 3, 4, 5, 6. And if we do that, then it has 8 electrons. So putting on those lone pairs, I used up 1, 2, 3, 4, 5, 6 pairs of electrons, which is 12 electrons. So I have no more electrons left. So step 5 doesn't apply because I don't have any electrons remaining. The last thing we are going to do is just double check our octets. Well, we already said that chlorine had its octets and hydrogen has its octets. We just have to double check that carbon also has its octet, and it has 4 bonds to it. Those 4 bonds in total have 8 electrons, so carbon also has its octet. So that is our Lewis structure for CH2Cl2. Let's practice another one. Our next practice had us doing NH3. So let's do NH3. Okay. So our first step is to count our valence electrons. So our valence electrons of nitrogen is 5 because they are in group 5. We're going to add to that, we have 3 hydrogens, each with 1 valence electron, so that's a total of 3 electrons from hydrogen. So in total we have 8 valence electrons that we are using to create the structure. So that's step 1. Step 2 was our skeletal structure. We put our central atom and put our surrounding atoms around it. So our central atom is nitrogen, and the surrounding atoms are hydrogen. Those 3 hydrogen. I don't have any more hydrogen. So even though we treat it like a box, if I don't have enough to go around, that's fine. I'm putting it on 3 of the 4 sides. Okay. So then I connect my surrounding atoms to my central atom with bonds. I now subtract the number of electrons I used to make those bonds from my total. So I used up 1, 2, 3, 4, 5, 6 electrons to make those bonds. So I'm subtracting off 6 electrons. And I have 2 electrons left. So step 4 tells us to place remaining electrons as lone pairs to complete octets or duets. Since our surrounding atoms are all hydrogens and they all have their 2 electrons associated with them, right? These 2 electrons go to that carbon, these 2 electrons go to that carbon, or hydrogen I should say, sorry, and those 2 electrons go to that hydrogen. They all have their duets, so all of those hydrogens have their duets and they're happy. So we've completed step 4 without having to place any remaining electrons anywhere. So we still have 2 electrons left. So we move on to step 5, which says place any remaining electrons after our octets are complete on surrounding as pairs on the central atom. So our central atom here is nitrogen. If we look at it as it is right now, it only has 6 electrons, right? It has 3 bonds associated with it, and those bonds all have 6 electrons in it, so it doesn't have an octet yet. But I have these 2 electrons that I can place as lone pairs on there. So I've placed those. I'm going to subtract those 2 electrons off because I've used them, and I have no electrons left. And now, since I placed those, I now have an octet on my nitrogen, okay, meaning my nitrogen also has its octet. So everything has an octet or a duet, and it's completely happy. So that is our structure for NH3. Okay, our last example was CH2O. So let's do CH2O. Step 1, count our valence electrons. We know that carbon has 4 valence electrons. We then have 2 hydrogens that each contribute 1 valence electron. And then oxygen has 6 valence electrons. Oxygen has 6 valence electrons in total. So altogether we have 12 electrons that we can use to draw our structure. Okay, our central atom is then going to be carbon with 2 hydrogens around it, as well as an oxygen. So we're just reading from left to right. So we see our central atom is carbon, 2 hydrogens, and an oxygen surround it. And we're going to connect those surrounding atoms to our central atom using bonds. Because I made 3 bonds, I used up 6 electrons, okay, because each bond has 2 electrons in it, meaning I have 6 electrons left. Step 4 tells us to take those remaining electrons and place them on our surrounding atoms as lone pairs to complete octets. Well, hydrogens don't need them. They all have their duets, so they're happy. Our oxygen only has 2 electrons, so we're going to do 1, 2, 3, 4, 5, 6 electrons to complete its octet. Okay, right? It has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. So because I placed those 6 electrons on oxygen, I have no electrons left. Okay. To erase this because I need that to be clear. Let me redraw my carbon here. Okay, so now we want to double check our octets. Well, we said the hydrogens both have their octets. We also said the oxygen now has its octet. And if we look at carbon, it only has 3 bonds. Meaning those 3 bonds only associate with 6 electrons. So carbon does not have its octet. So let's go to our rules. And step 6 says if octets are not complete, form multiple bonds by moving electron pairs. Okay, so we have to create a multiple bond, and we have to do that by moving electron pairs. So what I'm going to do is say that these 2 electrons from oxygen, that's an electron pair, okay? Those can be shared with carbon. Oxygen's going to say, well, I already have these 2, if I just give them to you in the form of a bond, I'm still claiming those, I'm still maintaining my octet, but that means you also have an octet. So oxygen's just being very polite and is allowing more electrons to be shared. So what that does is it creates a double bond. So CH, H, we have an O. One bond was made from the beginning, and I'm going to do a different color to show this, that purple bond was made from moving those lone pairs. Okay, so we made a double bond, and we can now check, well, we know our hydrogens have their octets. Oxygen now has 2, 4, 6, 8 electrons, so it has its octet. And carbon now has 4 bonds around it, meaning it has its octet. So by moving one pair of electrons, we are creating a double bond, and then that's completing our octet for carbon. We only move lone pairs to create multiple bonds if octets are not complete. Okay, I wouldn't move this lone pair anywhere on this nitrogen just because it was there. Okay, I wouldn't do that because all of my octets were complete. The only reason we moved these lone pairs in the first place was because carbon did not have an octet. So only do step 6 if octets are not complete. I oftentimes see students saying, well, I have these lone pairs, I could just make double bonds, but if my octets are already complete, the molecule doesn't want to form any double bonds. So just because you have lone pairs does not mean that you should form multiple bonds. Okay, you only form double bonds or triple bonds if octets are not complete. So we have to check our octets. That's why it's the very last step. Okay, let's keep on practicing. Keep on doing it. We're going to practice these until we master them. So, next up we have H2O. That's water. We've seen the water one before, but we're going to prove it now. We've been shown the Lewis structure. Now we're going to prove it to ourselves. So we have H2O. Hydrogen has 1 valence electron, but there's 2 of them. And we're going to add to that the 6 valence electrons of oxygen. That gives us a total of 8 electrons. Now here's a case where hydrogen is not going to be our central atom. Remember I said if hydrogen comes first, it is not the central. I'll write it again. Hydrogen will never be central atom. Okay, so oxygen is going to be our central atom here, and it's going to be surrounded by our hydrogens, which we're going to connect with bonds. Just going to move this over. Okay, so because I made 2 bonds, I used up 4 electrons, so I have 4 electrons remaining. My next step tells me to take any remaining electrons and place them on my surrounding atoms to form octets. Okay, hydrogen has 2, they're happy, so step 4 is done. We move on to step 5, which says place any remaining electrons on the central atom to complete its octet. So we have 4 remaining electrons. Oxygen only has 4 electrons surrounding it right now, so these excess 4 electrons are going to be placed on the oxygen as lone pairs to complete its octet. So now, in total, it has 8 electrons. 2 from the lone pairs, 2 from the bond. 4 from the lone pairs, 4 from the bonds. Okay. So that's our structure of water. That was the Lewis structure that we've been looking at all through this lecture, and we've just proved it, that is definitely what it looks like, and that's how we derived it. Our next example is O2, which is molecular oxygen. Okay, so O2 has 6 valence electrons, but there's 2 of them. So we have a total of 12 electrons to draw the structure. Since there's only 2 atoms in this molecule, those oxygens are just going to be next to each other. There is no one central atom. So my 2 oxygens are bound together by a single bond. My single bond used up 2 electrons. So I have 10 electrons left. So the rule then says any remaining electrons should be placed around the atoms to complete octets as lone pairs. 4 and 5, the difference between them is a little bit hazy right now because we don't have a central atom versus surrounding atoms. So we're just going to take these remaining 10 and place them on our oxygens. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I used up all 10 electrons and I have none left. So our next step is to check octets. This oxygen has 3 lone pairs and a bond, so it has 8. Okay, so that has its octet. This oxygen has 2 lone pairs and a bond, so that's only 6 electrons, so it does not have its octet. So if octets are not complete, we need to take lone pairs and we need to share them to create multiple bonds. So remember, we only create double bonds if octets are not complete. This oxygen has an incomplete octet. It does not have enough electrons around it. So the oxygen that does have 8 electrons around it is just going to share one of those pairs of electrons in order to create a multiple bond. So this becomes oxygen bonded to oxygen. This oxygen still has 2 lone pairs. This oxygen now has 2 lone pairs, because its 3rd lone pair is now shared in between the oxygens with a double bond. So we can double check. This oxygen now has 8 electrons around it, and this oxygen now has 8 electrons around it. Okay, so another one where we had an incomplete octet. So we had to share electrons and create a double bond. Okay. Our next example, or our last one for this slide, is CCl4. CCl4. So we have carbon first. Carbon has 4 valence electrons. Then we have chlorine. Chlorine has 7 valence electrons because it's in group 7A, but there's 4 of them, so we take 4 times those 7 valence electrons. So in total, I have 32 electrons. Again, feel free to type these things into your calculator and double check. It's always useful to double check. Doesn't hurt. So we have 32 electrons that we are going to share amongst this entire molecule. So we start with carbon in the middle. That's our central atom because it comes first. And it's surrounded by 4 chlorines, which we're going to bond to the carbon with bonds. So I made 4 bonds, which means I used up 8 electrons because each bond has 2 electrons in it. So after making bonds, I have 24 electrons left. So my next step says to take any remaining electrons and place them on my surrounding atoms to complete octets. We can see that each of our chlorines only has 2 electrons, so they all need an additional 6 electrons to complete their octets. So let's see if we have enough electrons to do that. So we're going to place them as lone pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I used up all 24 of my electrons to complete the octets of my chlorines. So all of my chlorines have their octets. Let's just double check that our carbon has an octet. It has 4 bonds around it, which means it has 8 electrons that are surrounding it. Because we have 4 bonds, each bond has 2 electrons. That's a total of 8 electrons. So carbon also has its octet, and that is our finalized Lewis structure. Okay, let's do a few more. What I want you to do is I want you to try these on your own. It's okay if you mess up. Okay, remember the point of trying these on our own is to get stuck and then use our videos to get unstuck so that we learn the topic even more. So I have 3 examples here that follow the same rules that we did before. Okay, so keep using those rules, get used to using those rules for drawing Lewis structures, and try these 3 on your own. The one comment I will make is about OCS, our last example here. I made the note that carbon is the central atom, so it is a carbon with a sulfur and an oxygen on either side. So that's your starting structure for what you're going to draw. So try drawing these Lewis structures, pause the video, and come back when you're ready to check your work. Okay, let's start off with our first example here. We have NCl3. So let's count up our valence electrons. Nitrogen has 5. Chlorine, there's 3 of them, and they each contribute 7 electrons. So in total, we have 26 electrons to place in this molecule. Nitrogen is our central atom here, and it's surrounded by chlorines, which we bond to the nitrogen with single bonds. I made 3 bonds, so I used up 6 electrons. Each bond has 2 electrons in it. So in total, I have 20 electrons left. My next step says to complete my octets of my surrounding atoms by placing my excess electrons as lone pairs. So all of my chlorines only have 2 electrons right now. They need another 6. So let's use some of these 20 electrons to complete our octets. So I have to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I used 18 electrons to complete my octets of chlorine. I have 2 electrons left over. Well, we can see that my nitrogen does not have a complete octet. It has 6 electrons around it. It needs 2 more. So we're going to take those 2 electrons and place them on the nitrogen to complete its octet. I've used up all of my electrons, and that is now my completed Lewis structure of NCl3, where everything has an octet. My next example is OF2. Okay, oxygen, let's count up our valence, has 6 valence electrons. Fluorine, there's 2 of them. We're going to multiply it by the 7 valence electrons in each fluorine for a total of 20 electrons in this structure. Oxygen is our central atom with fluorines around it that we connect to the oxygen with bonds. I made 2 bonds, so I had to use 4 electrons to create those bonds. So I have 16 electrons left over. I'm going to use those 16 electrons to complete the octets of my surrounding fluorines, because each fluorine right now only has 2 electrons. So they each need 6 more. So I do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I used 12 electrons to complete the octet of my fluorines, and I'm left with 4 electrons left. My fluorines both have their octets, but my oxygen does not. I only have 4 electrons around the oxygen right now. So step 5 tells us to use any remaining electrons and place them as lone pairs on the central atom to complete its octet. I put 2 lone pairs on the oxygen to complete its octet. That used up my last 4 electrons. I have no electrons left, and everything now has an octet in my structure. So that is my structure of OF2. My final example is OCS, where the carbon is the central atom here. So let's count up our valence electrons. I have 6 from the oxygen, 4 from the carbon, and 6 from the sulfur. So that's a total of 16 electrons in my structure right now. So if carbon was central, we had carbon that was bound to a sulfur and an oxygen. That used 4 electrons right there to create those bonds. So I have 12 electrons left. Those 12 electrons are going to be placed around my sulfur and my oxygen, since they both have incomplete octets. They only have 2 electrons, so they each need 6. So let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I used all 12 remaining electrons to complete the octets of my surrounding atoms, and I have no more electrons left over. But my carbon is missing 4 electrons. It only has 4 electrons right now. It needs 4 more. So what we're going to do is take some pairs from our sulfur and our oxygen, and we are going to create multiple bonds. So, like we've seen before, oxygen will give up one of its lone pairs to create a bond. And since sulfur and oxygen are in the same group, they're going to have similar properties. So if oxygen is polite and donates a lone pair, sulfur will also be polite and donate a lone pair. So this now creates a structure of OCS. Those now have double bonds, and I'm now 2 lone pairs on my sulfur and my oxygen. That doesn't change my octet because the oxygen still has 8, the sulfur still has 8, and the carbon now has 8. So my final structure of OCS is O double bond C double bond S, with oxygen and sulfur both having 2 lone pairs. So that's my final structure. Okay. Let's move on to something a little bit more tricky. What if we had 2 central atoms? Our rules don't really change much for if I have multiple central atoms. We still count up our valence electrons and everything and do our steps the same way. It's just now we have 2 central atoms to count and double check that we have octets for. So let's start off with H2O2, our first example. Remember, hydrogen cannot be our central atom, so oxygen is going to be central. So for H2O2, we're going to count up our valence electrons. I have 2 hydrogens, which each contribute 1. I'm going to add to that my 2 oxygens that each contribute 6. So I have a total of 14 electrons in H2O2. My oxygens are now my 2 central atoms, meaning that they are going to be bonded together. Okay? And each of those oxygens are going to have hydrogens coming off of it. Okay? What I can't draw is the hydrogen bonded to a hydrogen with an oxygen and an oxygen, because remember, this hydrogen now has 2 pairs or 2 bonds. This hydrogen now has 2 bonds, and hydrogen will only bond once. So this will not be our structure. So let's just erase that out of our minds. Hydrogen will never make more than 1 bond. Okay, so that's our structure. I've used up all of my atoms. And in doing that, I've used up 6 electrons, right? I have 2, 4, 6 electrons that are wrapped up in bonds. So I'm going to subtract those 6 electrons there. And I'm going to be left with 8 electrons left over. So my rule says to place my extra electrons on my surrounding atoms to create octets, but my surrounding atoms are hydrogens and they both have a bond to them, so they are happy with their duets. So my next step says to take any remaining electrons and place them on the central atom, or in this case atoms, to create their octet. So I have 8 electrons here. Each oxygen right now has 4 electrons, so they each need 4 more electrons to complete their octets. So let's take these 8 electrons and place them on our central atoms. So I placed all 8 electrons on my oxygens. I have no electrons left over, but if we look at our octets, that oxygen now has a complete octet, as does that oxygen. So that is our completed structure for H2O2. Our next example is N2F2. Okay, nitrogen, the 2 nitrogens are going to be our central atoms. So I have 2 nitrogens that each contribute 5 valence electrons, and I have 2 fluorines that each contribute 7. So in total I have 24 electrons. My nitrogens are going to be my central atoms. I'm going to bind them together with a bond, and they each have a fluorine coming off of them. So again, I've made 3 bonds, so I've used up 6 electrons. So I have 18 electrons left over. My fluorines have incomplete octets here, so I need to use some of these electrons to complete their octets. So we're going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I used 12 electrons to complete their octets, so I'm left with 6 electrons left over. Step 5 of our guidelines says to place any remaining electrons on our central atoms as lone pairs. Okay, so I'm going to say 1, 2, 3, 4, 5, 6. We're not going to separate those electrons up or anything. We're going to keep them as lone pairs. I've used them all up. I have no electrons left. Our last step is to just double check that everything has an octet. We know our fluorines have octets. My first nitrogen here has an octet, but my second nitrogen here does not. My nitrogen does not have a lone pair. It does not have an octet. So we're going to have to move a lone pair of electrons in order to form a double bond so it can have an octet. Now, because we have multiple central atoms here, we have some choices. So the fluorine could donate its 2 electrons there. We can create a double bond between the nitrogen and the fluorine. Or we could use the nitrogen on the other side that has 2 lone pairs, and it can now form a double bond in between that nitrogen. So we have some choices, but our choices can be changed if we remember some rules about specific atoms. So some rules about certain atoms. The first one, hydrogen will only bond once. The second one, halogens prefer to only bond once. Can they bond more than one time? Yes. if it's the only option, but if there is another option, then it will not bond more than once. So halogens prefer to bond only once. Oxygen likes 2 bonds and 2 lone pairs, which we may have been seeing as we have been drawing structures with oxygens. Okay, it has 2 bonds and 2 lone pairs. And carbon likes 4 bonds, no lone pairs. So carbon would prefer to have all bonds and no lone pairs at all. And finally, nitrogen likes 3 bonds and one lone pair. Okay, so oxygen likes 2 bonds, 2 lone pairs, nitrogen likes 3 bonds, 1 lone pair, and carbon likes 4 bonds, no lone pairs. You'll notice that they are in a specific order on your periodic table that expresses that, because halogens prefer to only bond once, and that means that they have 3 lone pairs. Okay, so if we look at our options here, if I were to do this first option, that would mean that my fluorine would have a double bond. It would have 2 bonds and 2 lone pairs, which is not what it prefers. If I use my second option, I would have a double bond between my nitrogen and my 2 nitrogen. Each nitrogen would then have 3 bonds and 1 lone pair, which is what it prefers. So we are going to go with option 2. Okay, so we follow just our general rules about certain atoms, and we say that the preferred structure would be, I'm going to draw this clearer down here, F, N, double bond N with an F. I have 2 lone pairs on my nitrogen, 3 lone pairs on all of my fluorines, and everything has an octet, and this structure follows my rules of certain atoms. Are there exceptions to these rules? Yes, we will see this oftentimes with larger molecules, if they just have a lot more electrons. We also see it if we have charges, that these rules can change. But typically for neutral atoms, if they're not too large of atoms, okay, they will follow these general rules. Hydrogen will only bond once. Halogens will also only bond once and have 3 lone pairs. Oxygen will bond twice and have 2 lone pairs. Nitrogen will bond 3 times and have 1 lone pair, and carbon will have no lone pairs and only bond 4 times. Okay, those are our general rules of specific atoms that we see often. Okay, so our final structure for NF2 is down here. We just have to make a decision about where our double bond would go. That appeases our rules. Okay, let's look at our last example. Si2H6. So Si, let's count up our valence electrons. Silicon has 4, and there's 2 of them. So there's 2 silicon atoms. Each atom has 4 valence electrons. We're going to add to that our 6 hydrogens, which each have 1 valence electron, and that is a total of 14 electrons that we're working with in this structure. I'm just going to draw a line down the middle here. Okay, so silicon is our 2 central atoms. We're going to bind those together to each other, and then they each have, what we can't tell is we have 6 hydrogens in total. Remember, this is like a square. Okay, so each of these is going to have a hydrogen on either side of it to complete its square. Okay, so hydrogen, hydrogen. I'm going to remove that square so that we can easily see our bonds. Okay, so I've made my bonds. Let's count how many bonds I made. 1, 2, 3, 4, 5, 6, 7. I made 7 bonds. Each bond has 2 electrons in it, meaning I used up 14 electrons. I'm going to subtract off 14 electrons. I have no electrons left over, so let's double check our octets and our duets. Well, hydrogen all have 2, so they're all happy. Each silicon has 4 bonds to it. 4 bonds means 8 electrons, meaning it has octets. So that is our final structure of Si2H6. Okay. Whew, that was a lot of Lewis structures. And don't worry, we have more moving on in this lecture. But I do want to just make a note about Lewis structures of ions. We've talked about ions a lot in our course so far, so we're going to talk about them a little bit more. So we can also write Lewis structures of ions. We can follow the same steps. We just have to account for the change in number of electrons in our first step, because the definition of an ion is that it has either accepted or removed electrons. So we have to account for that change in number of electrons. And in our first step, we're counting the valence electrons. So let's do the example of OH-. This is hydroxide. That's one of our polyatomic ions. So let's see, count up our valence electrons, and for ions, also account for the charges. Well, this is OH-. The minus means I've added 1 electron, right? -1 means I have 1 more electron than proton. So we count up for OH-. We say that oxygen has 6 valence electrons, hydrogen has 1, and I'm going to add my 1 extra electron. That one's coming from my charge. So in total, I have 8 electrons that I'm using to draw this structure. Okay, so let's draw our structure. We have O bound to an H. I used up 2 electrons to draw that bond. I have 6 electrons left. I'm going to place that on my atoms to complete their octets. Hydrogen has a duet, so it's happy. So those 6 electrons are going to go on the oxygen. I have no electrons left, and that oxygen now has an octet. So that is our final structure of OH. Now, when we're drawing our Lewis structures of ions, we have to represent the ion in the Lewis structure in some way. So what we're going to do is surround the structure in brackets and put the charge on the outside of those brackets. Okay, so the charge on OH- was -1, so I put a minus on the outside there. If this was -2, you would put a -2. If this was a +3, you'd put a +3. Okay, so when you note your charge on the outside of your Lewis structure, you want to put it on the brackets because that electron is being shared amongst the entire atom. If I didn't have the brackets, let me erase them really quick. If I didn't have these brackets and I just put them here, it would look like the electron was on the hydrogen, which it technically isn't, because the electron, that extra electron from the charge, is being shared amongst the entire molecule. Okay, so we put our brackets around it with the charge on the outside. Okay, let's do a few more. Now, what I want you to do with these is get used to accounting for the charges. So before we go into drawing the Lewis structures, what I want you to do is for each of these examples, count up the total number of electrons in the molecule, properly accounting for the charges. Okay, so remember, if it's negative, we add electrons. If it's positive, we remove electrons. So pause your video for a second and try that just to get used to counting up the total number of electrons for each of these ions. For our first example, NH4 plus, we're going to count up our valence electrons as is. So we're going to say nitrogen has 5. Hydrogen contributes 4, right? That's 1 times 4. And since we have a plus charge, it means we removed electrons. How many electrons did we remove? Well, there's no number next to it, so it's 1. So we subtract 1. So we get total number of electrons in the structure as 8. In ClO3 minus, we have Cl, which has 7. We have oxygen, there's 3 of them, and each oxygen has 6 valence electrons. It has a minus charge, so we have to add an extra electron. That's a -1, so we're adding 1 extra electron. You'll notice that these charges are essentially allowing us to not have an odd number of electrons, because if we had an odd number, then we wouldn't have enough to make pairs. Okay, and everything likes to be paired up. So these charges are useful for making sure that we have enough electrons to be paired up. Okay, for HCOO minus, we have 1 from the H, 4 from the carbon, 12 from the 2 oxygens, and 1 extra because it's a minus charge. So in total we have 18 electrons. And then Cn minus, we have 4 from the carbon, 5 from the nitrogen, plus 1 extra because it's a 1 minus. So we end up with 10 electrons. So let's start drawing these. Now that we have our total number of valence electrons, we follow our steps as is. So here we have NH4. We have N as our central atom. It's now surrounded by 4 hydrogens, and each of those will be a bond. Okay, so in making those bonds, I used up 2, 4, 6, 8 electrons. I have no electrons left. My hydrogens all have octet or duets. My nitrogen now has an octet because it has 4 bonds around it. So the last thing I have to do is surround this with a bracket and put my charge. So that is my structure for NH4+. So this is one of those exceptions to our rule about nitrogen. Again, we said it usually happens when there's an ion involved, so nitrogen is bonding 4 times. It's only allowed to do that because of the positive charge. Okay, let's try ClO3-. Let's see, we have Cl as our central atom. We have O's that surround it with bonds. So I've used up 6 electrons. I have 20 left. I'm going to use those 20, 2, 3, 4, 5, 6. I'm putting those on my oxygens to complete their octets. Okay, each oxygen only had 2. Now with their complete octets, or now with their lone pairs, I've completed their octets. I used 18 electrons to do that, so I have 2 electrons left. Those 2 electrons are going to go on my chlorine to complete its octet, right there. So now that everything has an octet, we're just going to surround this with brackets and put our charge on the outside. So we're following the same steps that we did in all of our previous Lewis structures, except now we are going to be representing our charge with brackets. Okay, next up we have HCOO. Here, hydrogen cannot be central. Carbon is going to be central, so it's the one that comes after the hydrogen. That's going to be surrounded by an oxygen, and a hydrogen. So I've used up 6 electrons to do that. I have 12 left. Okay, I'm going to place my extra electrons as lone pairs. I put them on the oxygens because the oxygens needed octets. My hydrogen did not, it had a duet already. So I've used up all 12, they're all gone, but my carbon does not have an octet. So since I have no electrons left, and I need to complete my octet, I'm going to take one of my lone pairs of my oxygens, I'm going to place it on my carbon to get a final structure of a double bonded O to that carbon. Now everything has a duet, my oxygens and now my carbon. So the final thing is place brackets around it and throw a negative sign on there. Our last example is Cn-. This is a good one. So we have C bonded to N. I used 2 electrons to do that. I now have 8 electrons left. So let's take those 8 electrons. Let's say 1, 2, 3, 4, 5, 6, 7, 8. Well, I used up all 8 electrons, making my lone pairs, but now my nitrogen only has 4 electrons around it. So carbon is going to donate one of its lone pairs there. So we're going to end up with C double bond N. That lone pair stays on that nitrogen. I then have my carbon double bonded with 2 lone pairs. But you'll notice that moving that, I now only have 6 electrons on my nitrogen. Let's see if there's more I'm going to do. So I don't have a complete octet yet. So what we're going to do is take another lone pair from carbon and move it down there. And we get C triple bond N with a lone pair on the nitrogen and a lone pair on the carbon. Okay, so nitrogen is still having three bonds and a lone pair. Carbon, not so much, but that's because we have an ion. So that's how we make triple bonds. By making a double bond, I didn't complete my octet, so I had to move another pair of electrons to make a triple bond. Okay, so that's our structure for Cn-. Okay. Let's look at these structures a little bit differently. So currently in these 3 structures, something is wrong with them. So let's try to figure out what is wrong. You're going to see similar problems to this on your ALEKS homework. So the first thing that we're going to want to do is count our valence electrons. And double check they are all there. And then our second thing is going to be to check our octets. Okay, so if we have C and N, we have carbon has 4, nitrogen has 5, there's a minus charge on there, so that's 10 total electrons. Let's count up our electrons in this structure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have all 10 electrons. So now let's check our octets. My carbon only has 6 electrons. My nitrogen has an octet. So the something wrong with our structure is that carbon has incomplete octet. That was just like one of our structures that we drew on our previous slide. We had a double bond and we needed another bond to complete our octet. Okay, let's look at our next one. We have CO. So carbon has 4, oxygen has 6. There's no charge, so in total we should have 10 electrons in this structure. Let's count our electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we do not have 10. So the issue with this structure is we have too many electrons. So we have 12 electrons total, but there should only be 10. Okay, let's do our next example. We have NOCl. Nitrogen contributes 5, oxygen contributes 6, and Cl contributes 7 valence electrons for a total of 18. Let's count up all of our electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All of our electrons are there. So let's just double check our octets. Chlorine that has an octet. Oxygen, that has an octet. So let's check our nitrogen. Nitrogen does not have an octet. So nitrogen has an incomplete octet. It's missing 2 electrons. Okay. Let's practice a little bit more. Let's try to identify the correct Lewis structure of carbon dioxide. Now we can do this a couple of different ways. We can go through each structure in our multiple choice options here, and we can figure out what's wrong with them. Or we could draw carbon dioxide using our rules and see which one matches up. You can do it either way. First off, we should always just double check our number of valence electrons. So carbon dioxide is carbon oxide 2. Remember, di is 2. So there's 1 carbon, 2 oxygens. So in total, we should have 4 plus 2 times 6. So we have 16 total electrons. Let's see if we can knock out any of these structures by counting electrons. Let's see, this one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. This one has too many electrons. Okay. This one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That one's valid. Okay. Let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That one does not have enough electrons. This one has 1, 2, 3, 4, 5, 6, 7, 8. Not enough electrons. And this one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Again, too many electrons. So this one had 16 electrons. Great, it's our only one left. But we can double check and keep practicing drawing our Lewis structures. So we know that there are 16 electrons in total. Carbon is our central atom that's bound to 2 oxygens. So that used up 4 electrons. So I have 12 left. Those 12 are going to go on my oxygens. Okay. That used up all 12 electrons, so I have none left. We see that our oxygens all have octets, but our carbon does not. So each oxygen is going to be nice and donate a pair of electrons. Since the carbon needs 4 more electrons, those 4 electrons are coming from the 2 lone pairs. So we get O, double bond C, double bond O, with 2 lone pairs on either oxygen, which corresponds to structure D. So we have multiple ways that we can double check it. The first one is right off the bat, just count your electrons, make sure that none of those have too many electrons or too few, and then double check with your own rules. Okay. On our last set of problems here, what I want you to do is pause the video and try to figure out what's wrong with these. Using our steps of first, count your valence, and check the molecule, and then check octets. So pause the video, use our 2 rules for each of these compounds to double check and see what is wrong with each structure. In our first example, we should count up our valence. So hydrogen, there's 2 of them, so that's 2 valence, plus the 6 in oxygen, that's a total of 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8, so they're all there. But our big thing that's wrong is that hydrogen can't bond twice. Okay, it wants a duet. It means 2 electrons. So that's what's wrong with our first structure. For our second structure, we have to count up our valence. So we have 4 from the carbon, 14 from the chlorines, and 6 from the oxygen. So in total, it's 24 electrons. Let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So we have too many electrons. Okay. And finally, in our last structure, we have Cl, which has 7, plus 6 from the oxygen, but there's a minus charge, so we have to account for 1 extra electron. So I should have 14 electrons in this structure. Right now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'm missing electrons. I have too few electrons, not enough electrons in my structure. So that ends our lesson on Lewis structures. Keep practicing these, get used to utilizing those rules. I definitely suggest making sure you can go through the entirety of the ALEKS homework and complete all of those problems and drawing those structures before moving on to our next lesson, which takes our Lewis structures and now we apply them. We do a few more exceptions and stuff like that. So we have to be able to master our Lewis structures first before moving on. So make sure you complete your ALEKS homework and fully understand Lewis structures before moving on to our next lesson.